Hello students, welcome to this lecture on binomial theorem. In this lecture, we will cover NCERT section 7.1 and 7.2. So let's get started. This is disclaimer. So first of all, we will introduce the basic concepts and historical context of the binomial theorem. Then we will focus on the binomial theorem for positive integral indices. This means we will looking at cases where n is a whole number. The theorem helps us expand expression like x plus y full to the power n into a sum of terms. Then we will understand Pascal's triangle. Okay, so it will help us to understand the binomial theorem better. Then in section 7.2.1, we will discuss the binomial theorem for any positive integer n. Finally, we will look at some observations of the binomial theorem. So students, first of all, make sure you are with your notebooks and pens ready. Okay? Let's start. First, we will discuss introduction. Okay, so we have learned how to find squares and cubes of binomials like a plus b and a minus b. For example, the square of a plus b is a square, okay, is basically is equal to a square plus 2ab plus b square. And a minus b whole square, this is equal to a square minus 2ab plus b square. Okay, so these formulas are known as identity in algebra. Okay, so these are fundamental algebraic identities taught in basic algebra. Okay, so that we have already learned in our previous class. Now, using them, we could evaluate the numerical values of numbers like 98 whole square. Okay, so 98 whole square, this can be written as 100 minus 2 whole square. Okay, and we can evaluate 999 to the power 3, and this can be written as 1000 minus 1 cube. Okay, however, for higher powers like 98 to the power 5, 101 to the power 6, etc., the calculations will become difficult. Okay, so here the calculation become difficult by using repeated multiplication. So for that, we need some shortcut to calculate these types of higher power. Okay, however, when we deal with higher powers such as 98 to the power 5 or 1100 to the power 6, here repeated multiplication becomes difficult. Okay, so this is where the binomial theorem comes in handy. So in this case, binomial theorem will help us to do calculation easier. Okay, so this difficulty is overcome by a theorem known as binomial theorem. It gives us an easier way to expand a plus b whole to the power n, where n is an integer or a rational number. Okay, so in this chapter we will focus on the binomial theorem for positive integral indices. Okay, this means we will looking at the cases where n is a positive whole number. Okay, so let's see further. Now we will look at some identities that you already know. Okay, so we are familiar with the following algebraic identities like a plus b whole to the power 0 is equal to 1. Okay, so now we will look at some identities here that is actually a plus b whole to the power 0. This is equal to 1. Okay. So we all know if we have a non-zero number, okay, and if power of that non-zero number is 0, then that will always give us 1. Okay. And then a plus b whole to the power 1. This is equal to a plus b. Next, we have a plus b whole square. This is equal to a square plus 2ab plus b square. Now, let's examine a plus b whole cube. This is equal to a cube plus 3a square b plus 3ab square plus b cube. Finally, we have a plus b whole to the power 4. This is equal to a to the power 4 plus 4 times a cube times b plus 6 times a square into b square plus 4 times a into b cube plus b to the power 4. Okay. So this pattern is crucial for understanding the binomial theorem. Okay. So these identities we all know, okay, already in our earlier classes. Okay. So now further we will understand binomial theorem for any positive indices. Okay. So in expansion, you can see that the total number of terms is 1 more than the index. Okay. So if we have index 0, then number of terms is 1. Okay. If we have index 1, then number of terms is 2. Okay. When we have index 3, that case we have number of terms is 4. Okay. So 3 plus 1, that is 4. So we observe here the total number of terms is 1 more than the index. For example, if the index is 2, then there will be 3 terms. If the index is 3, then there will be 4 terms. So let's look at an example. Okay. So for example, in the expansion of a plus b whole square, here number of terms is 3, whereas the index of a plus b whole square is 2. Okay. Then look at second important pattern. Okay. So the second important pattern is that of the power of the first quantity. A decreases by 1 in each term. Okay. So for example, in a plus b cube, here starting from a cube, okay, starting from a cube, then a square, then a, and finally the power of a becomes 0. Okay. So here powers of the first quantity a go on decreasing by 1. Okay. So we observe this point. Similarly, the power of the second quantity, that means the power of the quantity b increased by 1 in the successive terms. Okay. So in the beginning, b has power 0, then b has power 1, then b has power 2. Okay. And continuing like this until the last term. So for the second term, for the second quantity b increasing by 1, for the first quantity a decreasing by 1 in the successive terms. Okay. Clear? I hope it's clear to all of you. So in each term of the expansion, the sum of the indices of a and b is the same and is equal to the index of a plus b. Okay. So in each term, the sum of the indices of a and b is the same, and this sum equals to the index of a plus b. Okay. This is a consistent pattern that you should remember. Okay. Now, it's difficult to directly multiply and find a plus b raised to the power 4. Okay. So you can expand a plus b whole to the power 4 by direct multiplication, a plus b whole cube times a plus b. But this is difficult to calculate. Okay. So for that, we need binomial theorem. Okay. So think about how time consuming it would it would be to expand expression like a plus b whole to the power 12 or 98 to the power 5. Okay, so that's why we need a shortcut method. So what is the shortcut method for to do this? That is basically binomial theorem. Okay, so binomial theorem will give us shortcut method to expand a plus b whole to the power 12 or 98 to the power 5 or for higher powers. Okay, so now we will see some objective. Okay, so let's see. Our objective today is to establish a general formula known as the binomial theorem. Okay, so binomial theorem provides a systematic way to expand expressions of the form a plus b whole to the power n, where n is any positive integer. Okay, and this will greatly simplify our calculations. Okay, so for calculating a plus b whole to the 12, 98 to the 5, okay, we faced problem. Okay, and this problem will solve binomial theorem. So now we are going to establish binomial theorem for the expansion of a plus b whole to the power n, where n is the any positive integer. Okay, now look at an expression consisting of two terms connected by plus or minus sign is called a binomial expression. Okay, so this is the definition of binomial expression. So if we have an expression and if this expression consists of two terms connected by plus or minus sign, this expression will call binomial expansion. Okay, binomial expression. For example, expressions like x plus a, 2x minus 3y, 1 by x minus 1 by x cube, 7x minus 4 upon 5y, okay, etc. So these expressions are all binomial expressions. Why? Because in these expressions we have two terms, okay, and they are connected by plus or minus sign. Okay, so this is why these expressions are all binomial expressions. I hope it is clear to all of you. Let's learn about Pascal's triangle. Okay, so this table shows Pascal's triangle. So in this table, you can see when index of binomial is 0, that case coefficient of the various terms is 1. Okay, only 1. And when index of binomial is 1, then coefficients of various terms are 1 and 1. Okay, and when index of binomial is 2, that case coefficient of various terms are 1 to 1. Okay, and similarly for index 5, the coefficient of various terms are 1, 5, 10, 10, 1. Okay, so this triangle's forms is called Pascal's triangle. Okay, now we will see some concept related Pascal's triangle. So this is a triangular array where each number is the sum of the two numbers above it. Okay, so we call this Pascal's triangle. And this triangle provides us binomial coefficients which are used in the expansion a plus b whole to the power n. Using this, we can expand complex expressions. Okay. Now we will look at the construction of this triangle. Start with 1 at the top for index 0. Okay, so here for index 0, coefficient of various terms is 1. Okay, there we will have only one term and the coefficient of that term is 1. And the first second row, okay, for this next row for index 1, so for index 1, there we have two terms. Okay, so coefficient of these two terms will be 1 and 1. So in the second row, we have 1, 1. as we move to the subsequent rows, each row begins and ends with 1. Okay, so you should note here, each row begins and ends with 1. So this pattern is consistent throughout the triangle. Okay, and every other number in a row is the sum of the two numbers diagonally above it in the previous row. Okay, now this table shows Pascal's triangle. Okay, this triangle provides the coefficients for binomial expansion. So look at this table. Okay, so in this table we have index, that is n, coefficient in a plus b whole to the power n, and Pascal's triangle. Okay, so try to observe this table. Okay, and try to understand this table. Okay, so from this table you will get coefficients for binomial expansion a plus b whole to the power n. Now let's focus on how Pascal's triangle provides the coefficients for binomial expansion. Okay, so for example, for binomial expansions, 2x plus 3y whole to the 5. Okay, so Pascal's triangle provides the coefficient for the binomial expansions like 2x plus 3y whole to the 5. So we can use the coefficients from the fifth row of the Pascal's triangle. So each row of the Pascal's triangle corresponds to the expansion of a plus b whole to the n, where n is the row and index starting from 0. Okay, this means the first row corresponds to a plus b whole to the power 0. The second row corresponds to a plus b whole to the power 1, and so on. Okay. For example, let's consider the row for index 5. Okay, so this row will give us the coefficients needed for expanding a plus b whole to the power 5. The row for index 5 in Pascal's triangle is 1, 5, 10, 10, 5, 1. These numbers are the coefficient for 2x plus 3y whole to the power 5. So let's write out the expansion using these coefficients. So 2x plus 3y whole to the power 5, this is equal to 1 times 2x to the power 5 into 3y to the power 0 plus 5 times 2x to the power 4 into 3y to the power 1. Okay, plus 10 times 2x to the power 3, 3y to the power 2. Okay, plus 10 times 2x to the power 2 and 3y to the power 3, plus 5 times 2x 5 times 2x to the power 1 into 3y to the power 4, plus 1 times 2x to the power 0 into 3y to the power 5. Okay, so one thing I hope you observe, that is here for the first term 2x, here the power of first term 2x is decreases by 1 for the subsequent terms. Okay, and the power of the second term, that is for 3y, it increases by 1 for subsequent terms. Okay, so this is the expansion, binomial expansion for the expansion of 2x plus 3y whole to the power 5. Okay, and here Pascal's triangle helps us to write out the expansion using these coefficients. Okay, like this. Now, calculating higher powers using Pascal's triangle can be tedious if done manually. Okay, so this is the problem to use Pascal's triangle. So for higher powers, we cannot find Pascal's triangle. Okay, and for that we cannot find binomial coefficients. So this is good for lower power. Okay. But if you have higher power, more than 5, that case it's tedious. Okay. Now, so to overcome this, we use the binomial theorem, which uses combinations NCR to directly find the coefficient. Okay. So we will overcome Pascal's triangle for higher power expressions. Okay. So for that, we will use the binomial theorem, and binomial theorem uses combinations like NCR. Okay. To find the coefficients. So let's look at the formula for combinations. That is NCR equal to n factorial upon r factorial into n minus r factorial. Okay. So we will use this formula to find coefficients in binomial expansion, where n is the power of the binomial. Okay. The row index in Pascal's triangle. Okay. That is n here. And r is the terms position in the expansion starting from 0. Okay. This means that each number in Pascal's triangle can be represented in the form of NCR. For example, in the second row of the Pascal's triangle, we have 1, 2, 1, okay, which can be represented as 2C0, 2C1, 2C2. Now look at here this table. Okay, so here let's see how we write the fifth row of Pascal's triangle. Okay, so the numbers are 1, 5, 10, 10, 5, 1. So these coefficients are very important because we can use them to find the expansion of x plus 5 raised to the power fifth power. Okay, so here we have written in terms of combination. So for instance, the row of index 5. Here the coefficients are 1, 5, 10, 10, 5, 1. Okay, so this can be written as 5C0, 5C1, 5C2, 5C3, 5C4, 5C5. Okay, so this technique helps us find coefficients for any power of n without constructing the entire Pascal's triangle. Okay, so it makes calculations easier to us now. Now, connection to binomial expansion. The numbers in Pascal triangle have a direct connection with binomial expansion. The numbers in the row corresponding to index n are the coefficients nc0, nc1, nc2, and dot 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 ncn. For example, when n equals to 4, the coefficients are 4c0, that is 1, then 4c1, that is 4, 4c2, that is 6, 4c3, that is 4, and 4c4, that is 1. Okay. So using these coefficients, we can expand a plus b whole to the power 4. Okay, as 1 times a to the power 4 plus 4 times a to the power 3 into b to the power 1 plus 6 times a to the power 2 into 2 b to the power 2 plus 4 times a to the power 1 into b to the power 3 plus 1 times b to the power 4. Now, if we want to find the expansion of 2x plus 3y whole to the power 12. So we have first requires to get the row of the index 12. So this can be done by writing all the rows of the Pascal's triangle till index 12. So this is slightly lengthy process. So the process, as you observe, will become more difficult if we need to expansion like involving still larger powers. So we are trying to find a rule here that will help us find binomial expansion without without writing out all rows of Pascal's triangle. Okay, this is very useful when dealing with higher powers. So for this, we make use the concept of combinations studied earlier in our previous chapter to rewrite the numbers in the Pascal's triangle. And we know that NCR equal to n factorial upon r factorial times n minus r factorial for 0 less than equal to r less than equal to n, comma 0 less than equal to r less than equal to n. Okay, and n is a non-negative integer. Also, NC0 equal to 1, and this is equal to also NCN. So creating the triangle is impractical for large values of n. Now look at binomial theorem for any positive integer n. Okay, so a and b are two real numbers. Okay, and n is a positive integer. So now let's see how the expansion works. Now let's look at the binomial theorem itself. So it states that a plus b whole to the power n can be expanded as nc0 a to the power n plus nc1 a to the power n minus 1 times b plus dot 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 plus ncn b to the power n. Here ncr represents the binomial coefficient. And a and b are two real numbers and n is a positive integer. Okay, where ncr equal to n factorial upon r factorial times n minus r factorial for 0 less than equal to r less than equal to n. Now we will see proof of binomial theorem by mathematical induction. So proposition Pn such that a plus b whole to the power n is equal to summation k equal to 0 to n nck a to the power n minus k times b to the power k for n belongs in natural number. So base case for n equal to 1. So left hand side a plus b whole to the power 1, this is equal to a plus b. Right hand side summation k equal to 0 to 1 1ck into a to the power 1 minus k times b to the power k, this is equal to 1c0 to a to the power 1 times b to the power 0 plus 1c1 a to the power 0 into b to the power 1. Okay, and this is simply equal to 1 into a plus 1 into b, this is equal to a plus b. Since LHS equal to RHS, so P of 1 is true. Now we'll see inductive hypothesis. Assume P of m is true for some positive integer m. So P of m such that a plus b whole to the power m equal to mc0 a to the power m plus mc1 a to the power m minus 1 times b plus dot 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 mcm b to the power m. Now we will see inductive step. So now we'll prove P of m plus 1 is true. So we need to prove a plus b whole to the power m plus 1 equal to m plus 1 c0 a to the power m plus 1 plus m plus 1 c1 a to the power m into b plus dot 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 plus m plus 1 c m plus 1 b to the power m plus 1. Now start with LHS. So a plus b whole to the power m plus 1, this is equal to a plus b times a plus b whole to the power m. Now using the inductive hypothesis, a plus b whole to the power m plus 1, this is equal to a plus b times mc0 a to the power m plus mc1 a to the power m minus 1 times b plus dot 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 mcr a to the power m minus r b to the power r plus dot 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 plus mcm b to the power m. Now multiply by a and b. So now it will become mc0 a to the power m plus 1 plus mc1 a to the power m times b plus dot dot mcr a to the power m a and b. Okay, so you will get a mcr a to the power m plus 1 minus r b to the power r plus dot 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 and plus mc0 a to the power m b plus mc1 a to the power m minus 1 into b square plus dot 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 mcr a to the power m minus r to the, into b to the power r plus 1 and dot dot dot. Okay. Look students, here we are grouping terms that have the same powers of a and b. So this grouping is important so that we can simplify further. mc0 a to the power m plus 1 plus mc1 plus mc0 a to the power m times b plus mc2 plus mc1 times a to the power m minus 1 times b square plus dot mcr plus mcr minus 1 a to the power m plus 1 minus r into b to the power r plus dot mcm into b to the power m plus 1. Now apply Pascal's identity. We know ncr plus ncr minus 1, this is equal to n plus 1 cr. Therefore, mcr plus mcr minus 1, this is equal to m plus 1 cr. So also mc0 is 1 and m plus 1 c0 is also 1 and mcm equal to 1 equal to m plus 1 c m plus 1. Then substituting this into the expansion, you will get m plus 1 c0 a to the power m plus 1 plus m plus 1 c1 a to the power m into b plus dot 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 m plus 1 c m plus 1 b to the power m plus 1. And this is exactly right hand side for p of m plus 1. So we can now conclude that by the principle of mathematical induction, the theorem holds for one natural number n. Now we will illustrate this theorem by expanding x plus 2 whole to the power 6. So let's see expansion x plus 2 whole to the power 6. This is equal to 6c0 x to the power 6 plus 6c1 x to the power 5 into 2 plus 6c2 x to the power 4 into 2 square plus dot dot 6c6 into 2 to the power 6. And it implies x plus 2 whole to the power 6. This is equal to x to the power 6 plus 12 times x to the power 5 plus 60 times x to the power 4 plus 160 times x to the power 3 plus 240 times x square plus 192x plus 64. Thus, x plus 2 whole to the power 6, this is equal to x to the power 6 plus 12 times x to the power 5 plus 60 times x to the power 4 plus 160 times x to the power 3 plus 240 times x square plus 192x plus 64. Now, we will see some important observations. Here, number of terms. The total number of terms in the expansion of a plus b whole to the power n is n plus 1, which is one more than the index 1, n. Now, sum of indices. In every term of the expansion, the sum of the powers of a and b is equal to n. For the term ncr, a to the power n minus r b to the power r, the sum of the powers is n minus r plus r is equal to n. Now see symmetry of coefficients. The binomial coefficients of terms equidistant from the beginning and the end are equal. Okay. Here note this property: ncr equal to nc n minus r. Now let's take an example. In a plus b whole to the power 6, the coefficient of the second term 6c1 is equal to the coefficient of the sixth term 6c5, since 6 minus 1 is 5. The power of a and b. In successive terms, the power of a decreases by 1 while the power of b increasing by 1. That is, the power of a is n in the first term, then n minus 1 for second term, and so on, ending with 0 in the last term. At the same time, power of b is 0 in the first term, 1 in the second term, and 2 in the third term, and so on, and ending with n in the last term. I hope these observations are clear to all of you. Now, see, sum of all coefficients, sum of all the binomial coefficients is 2 to the power n. That here you can see in 1 plus x to the power n, here nc0 plus 1, nc1x plus nc2 x square plus dot ncn x to the power n. Here let x equal to 1. It implies 1 plus 1 whole to the power n. This is equal to nc0 plus nc1 plus nc2 plus dot ncn. And it implies 2 to the power n. This is equal to summation k equal to 0 to n nck. The coefficients in the expansion follow a certain pattern known as Pascal's triangle. Now see some common misconceptions. Remember that a plus b whole to the power n not equal to a to the power n plus b to the power n for n equal to 1. Okay, this theorem shows there are n minus 1 intermediate terms. That's all for today's lecture, and thank you very much to all of you.